Well, welcome back everybody. This is the second video I'm making on converting MakeMore into C from Python. So before we get on to newer material, I just want to review what we did in the previous video. And I put up some notes here so we can all go through them together. We started out with 32,033 names. We delimited each name with periods, and then we split this whole list into bigrams. 2 characters per bigram, so X is our input character and Y is our target or our label. So we ended up with 228,146 bigrams. So that's like pairs of characters in our data. We then created an array of 27 by 27. Why 27 by 27? Because our alphabet of our data consists of 27 characters. Like the 26 lowercase letters of the English language plus the period. So that's 27. So the total possible bigrams we can have is 729. But when we added up all the duplicate bigrams in our list here of 228,000, we ended up with 627 unique bigrams. So there were some pairs of characters in our list of names that just don't exist. You know, maybe I don't know, J followed by an X or something like that. That might not exist in our list of names. So we're stuck with 102 bigrams that have a 0 count. So when we have our 27 by 27 array, we ended up with 102 elements of that array that have a 0. And we really don't want to have zeros in there, so what we do is we do this procedure called smoothing. So we added 1 to each bigram, so that even these 102 bigrams that were 0, they all become 1. And all of our other bigrams, the 627, they all become one extra. Of course, the smoothing, we could have added 2 or 3 or 4 to all of the bigrams, or we could have added a dozen to each bigram. But the problem is that as the word smoothing suggests, the higher the number that you add, the more smooth the data becomes. So it doesn't really, in fact, all of the numbers become very, very close to one another. And so that's probably not a good idea. So then we normalize each row of the array by dividing each bigram count by the sum of the counts in the row. And this basically gave us probabilities, or actually likelihoods, I guess you could call it. The sum of each row is now 1. We then use these probabilities to randomly create new names. So what we can do is we can go through our array here of so-called probabilities, and we can select letters randomly based on those probabilities to make up new names. We'll talk more about that a little bit later, because we use this same technique for of generating new names. We use that same technique over and over again. We also compute the loss of our system, because we need some way to measure how good this system is, the quality of the system. So basically, when you look at one row of this array, let's say the row of the letter J. If you look at the row of the letter J, you're basically looking at a probability distribution of what comes after a J. Okay. So to get the total probability, we need just to multiply all of those probabilities. But multiplying all those probabilities will give us a real tiny number. In fact, chances are we might even underflow a float and end up with nonsense, or end up with something we can't use. So rather than multiplying the probabilities, all the probabilities in one row, what we do is we add the logs of all of the bigram probabilities. So I'll just say of all the, maybe I should add in here, of the bigram so we add the logs of all the bigram probabilities, and this gives us a negative number. But that's better than having an underflow, which will end up useless. So then we negate the log likelihood, so we end up with what's called the negative log likelihood. And then we divide the negative log likelihood by the number of bigrams. In our case, we ended up with a loss of about 2.45 for this first model. Okay, so let's just go. I just want to just demonstrate again the bigram counts and and show you the plot file I made. So let me bring that over here. And so I'll say GNU plot, and I think it's bigram counts.txt is our text file. Oh no, sorry, that's the wrong one. It should be bigram counts.gp. So this is basically our 27 by 27 table. And you can see in this table here, these are all the counts. And remember, if we normalize these counts by taking, we sum up the whole row here, we sum up the whole row, and then we divide each number here by the sum. And we end up with each row is now a probability row, or a likelihood row, I guess you could call it. Okay. And you notice all the ones in here, all the ones here are the ones that were zeros. And the reason they're ones now is because of smoothing. We added one to each one of these guys. Okay, so that's that. And the plot, I didn't show you the plot. Those of you who are interested in the plot program, you can look at, we can show you the bigrams counts.gp. That's what our plot program looks like, the GNU plot program. Okay. Okay. So let's move on to new stuff now. Moving on to new stuff, I want to bring up a diagram I put together for you. Let me see if I can find it here. Okay, here it is. So what we're going to do now is we're going to switch to a very simple neural network framework. So we're not going to be just using counts, like manually counting up things and changing them into probabilities. Instead, what we're going to do is we're going to use a primitive neural network, and we're going to use gradient descent, which gives us a method of computing the probabilities iteratively. So instead of just counting all the counts, we're going to try to determine the counts in an iterative fashion using backpropagation. So let's see how we're going to do this. We're going to start with our bigrams that we had here. For example, we had Emma followed by Olivia. So you can see dot E is our first bigram. And encoded, we end up with a 0 and a 5 because E is like a 0 is a period and a 5 is the letter E. So our second bigram is EM, so that's a 5 followed by 13, and M is encoded as a 13. MM is 1313, MA is 131, A dot is 10, and then we go into a new name which is dot O for Olivia, the second name in our list, which is 015, and so on. So these vectors here, you can think of them, I guess, as vectors or one-dimensional arrays. They are really long because the length of these arrays is the number of bigrams we have, which is like 228,000. So we have a lot of bigrams. So once we encode these guys into integers, we then have to perform this operation called one-hot encoding. So we have to encode them a second time. And this time we're encoding them into basically into rows of ones and zeros. So for example, we're going to have here 27 binary digits in the first row. In fact, every row will be 27 binary digits. But the way this one-hot encoding works is, for example, a 0 means we put a 1 in the 0th position. And all the other 26 digits or binary digits are all 0. Okay, so we're encoding X here. So the next value in X is a 5, which is the letter E. So you notice we got 0, 1, 2, 3, 4, 5. So we encode the E as a 1 here. Okay, so we do that for all of the bigrams. So this one-hot array here, actually I'll bring my tablet here so I can write on it. You can see this oops, let me hang on here. I don't want to do that. What I want to do is I want to say that this table here is going to be basically the number of bigrams by 27. So this is the number of rows. So it basically goes on and on and on. Okay, as these ones do as well. These guys go on and on and on for the length of the number of bigrams we have. But you notice that our table here of weights is still 27 by 27, and we initially we just put random numbers in there. So we have 27 by 27 random numbers. So this was basically equivalent to our end table in our previous video. And so again, instead of counting, we're just going to try to work out what this weight table is in an iterative fashion using backpropagation and gradient descent. Okay, so we have here our one-hot. These are our inputs. And these are our outputs. Okay, so again, this is going to be very long, and it's going to be filled with not binary digits, but this is going to be floats. Okay, and what we want to do is we want to use backpropagation with a gradient descent to actually kind of, how should I put it? we'll go backwards here over and over again like this until we can get these answers to be close to our original data here. This is what we're actually expecting. Okay, we're expecting to get the answers like this in this particular table. So we go over and over and over again, and as we do that loop and we go round and round, the numbers in here will start to approach the counts that we used in the first video. So I hope everybody kind of understands that. Okay, so what we're going to do is, let's show you the forward pass anyway. Let me get rid of this thing. I don't want to save it. Discard. What I want to do is I'll just bring it in again as a fresh picture here. Hang on. So our forward pass is, we're going to use this formula here, so that the Y predicted is going to be the weights times the one hot X plus B. B is a bias, but in our case here, B here is equal to 0. So we're not using B. So what we're doing, in order to get this Y predicted, this guy here, we're going to say Y predicted is going to be equal to our weights here times our X, our one hot encoded X. But if you notice the dimensions here, when we want to, this is, by the way, matrix multiplication. Okay, this is matrix multiplication. In order to do the matrix multiplication, if you look at W is 27 by 27, and we want to multiply that by X, which is the number of bigrams by 27. Okay, so you can see if we multiply W by X, it doesn't seem to work, because we need, in order to do matrix multiplication, the number of rows must equal to the number of columns in the second array. And the number of rows here, well, actually it does work, but we have to flip it around. In other words, we have to do something like this. We have to go, and instead of doing W times X, we should do X times W. So we end up with number of bigrams by 27, and we're multiplying that by 27 by 27. So these two inner guys kind of cancel each other out, and we're stuck. We end up with number of bigrams by 27. So this guy up here, this is number of bigrams. That's our result output. Okay, so that's a forward pass. Once we do that forward pass, we have to figure out what our loss is, and then our loss will tell us how much we have to change our weights. So we have to figure out what our change in our weights is going to be for the second pass. But in any case, let's go through the Python program that actually does this forward pass. Let's take a look at it. Let me delete this guy here, discard that. All right, let me get that Python program up here. Whoa, MM2. Sorry about that. Okay, so our Python program is, let's take a look at it. Where is it here? do it 1a pi. Here it is. So let's do a little walkthrough of this. This is the forward pass of the Python program to try to get our predicted y values. So when you look at this, the first thing you'll notice is that I had to add in these three lines. And again, the reason I'm adding those in is because the random numbers I'm using, I want them to be exactly the same random numbers that I'm using in my C program. And that way I can compare my C program output. I can compare it to the Python program output. So I generate random numbers here by putting together this little MakeRandom function, which I wrote. Again, I'm not a Python person, so probably people are going to find a lot of shortcuts that they can use to make the thing more efficient. But anyway, what I did was I said, okay, if I want a table here of so many rows and so many columns, then I can fill them up using this append function. I have an array here, v, and I can append a random number here. And I'm using just a Gaussian distribution, which is like a normal distribution. And I think the 1.0 I think represents a standard deviation of 1. So I do this loop here, and I generate row times column random numbers, and I fill it into this this array here. And then I change it into a tensor by saying torch.tensor, and then I return the view as rows and columns. I don't think I really need to do that, but for me it makes more sense. I think I can just say return v without this, and I think it should still work. But anyway, so that function I use just to make random numbers. And again, these random numbers are the same ones I'm going to be using in my C program. So now we go and we open up the text file. This is the 32,000 names. We join them all up. And we also create these two functions here, string to integer and integer to string. Okay. And then we go in and we create here x and y. Just like I showed you in the diagram a few minutes ago, I had x and y. So what we're doing is we're creating these two vectors, these really long vectors, 228,000 rows more or less in a single column. So we take each word, we surround it by periods, and then we go through this for loop here, creating our x and y vectors. Okay. All right. So what do we do then? Well, here it tells us how many we have, how many x's we have. It should be about 228,000 or something like that. And again, I had to comment out the random number generator that is used in the original Python code. Instead, I'm using my own MakeRandom function here to make the initial weights. So these initial weights, these random 27 by 27, these numbers, and I've checked them, they are exactly the same numbers as I'm getting in my C program. Then I also tell it here that this variable here requires a gradient. That's for back propagation. We're going to need to know the gradient of that array, or the delta W. So then we go to make some new names here. Well, not new names, sorry, this is not making new names. This is going through, I'm going to go through 150 forward passes. And with each forward pass, I'm going to do a backward pass to update my weights. So you can see here, this is where he does the one hot encoding. Just uses this one hot function that's available here. So he encodes all of this X here. Let's say if it was a 5, he encodes it into 27 binary digits. It's zeros and ones. So with a 5, if X is a 5, then the 5th position will be a 1. And again, they will be floats. So it'll be like 1.0. Then what we do is we do the multiplication. We multiply that by that. And you see in Python, you just specify this operator and it does array multiplication. It figures everything out for you. You don't have to worry about anything. Okay. Then what we do is we exponentiate the log counts to get counts using the exp function. And then what we do is we normalize the counts here by dividing each count by the sum of the row to get probabilities. And once we get probabilities, then we can figure out what our loss is. And remember, the loss is basically it's basically just the, I guess you could say, the sum of all the negative log likelihoods divided by the count of the bigrams. Anyway, the interesting feature here is once we print out the loss, which is like 2 point something, we then go into a backward pass. In the backward pass, they zero out all the gradients, and they just call this function called backward. And this does all the calculations for us automatically. I mean, when I first saw this, to be honest, I was mesmerized. I was floored because this backward function was written, I believe, in 2016 by the Meta people, Facebook people, I guess. And it does all the back propagation for us. Really, no matter how complicated our neural network is, it will figure things out for us. Once we figure out what the change in W is, we can then update W by adding the gradient. So the way it works is, let me see if I can just show you here. Get my little drawing pad out here. You can think of it like this. We have our 27 by 27 weights, and when we go through the forward pass, we end up getting a loss. And what we can do is we can then compute here a delta W. So these are small changes to our weights in order to make the loss less. So after we take our X array here, X encoded, we multiply that, we end up with our Y predicted answers. We can then check our loss and we say, oh, we better adjust our weights slightly to get a better loss. So what we do is we do this thing called gradient descent or back propagation, we go backwards and we end up with this. I guess that's, I should have, like, instead of just saying like delta W, the changes we need in W to make our loss better, it's really a partial derivative. What we need is the loss with respect to W. We need to work out this derivative. We'll do that a little bit later, and I'll show you how it's done. But the whole point is that we go through this forward pass. In our example here, we're doing it 150 times. We're going through the forward pass, and every time we go through a forward pass, every loop we do, we then create a brand new delta W, which we can use to update. So we use it to update our original W. And then we make another forward pass, figure out what our delta W's are, and update our weights again. And we keep doing that 150 times. And hopefully our loss will get, every step our loss will get better and better, or less and less and less all the way. So that's the idea behind this forward pass. And this Python function here, again, it does all the work for us. It's just an incredibly I don't know what I can say, fantastic function that just does everything for us. And then, of course, we go into our MakeMore loop to make 20 more names. So after we've iterated 150 times here, updating our loss all the time, updating our weights, going through back propagation, gradient descent, all this kind of stuff, we can then go through and we can generate some names, because at this point, at line 52, at this point, our weights should be pretty close to counts. I think pretty close to counts. So what we're going to do is, in order to sample our W, we have W, we want to do a sample now, 20, we want to generate 20 names. We start with row 0. We're going to pick a random number in row 0, and that random number is we're going to determine our starting character, basically. Our starting character is going to be a period, which is 0. Okay. So we do one hot encode here, and then we multiply that by W. But remember, this time we're only using one. Instead of having 228,000 bigrams, we only have one bigram here. We only have one bigram. So we're basically multiplying a vector by an array. Okay. Now, I could have, here's something else that's interesting. I could have said, let's get our counts here by using the exponentiation of the log counts, and then we can get our probabilities by dividing the counts by the sum of the row. So I could have done these two lines, but instead of doing these two lines, I'm going to introduce another function here called softmax. Okay, see here I introduced the one hot function here, but now I'm going to show you this softmax function that's available to us. And the softmax function basically does these two lines in one function. It actually exponentiates the log counts, and then it normalizes the counts into probabilities. So it produces, in our case here, it produces a one-dimensional array of probabilities. And then we use that one-dimensional array of probabilities as a probability distribution that we're going to sample. So Again, I'm not using the multinomial function that's part of PyTorch. Instead, I'm going to use the multinomial function that's part of the GNU scientific library. Okay. So I take the probability vector basically, and I flatten it, and I then create it in a VVV here is then created or make it into just a basic NumPy list. Because this, you see, the multinomial torch function, it requires a probability distribution here, P, that's a tensor. Whereas this multinomial function requires just a NumPy list. Okay, so that's why I had to go kind of kludge this to produce this so I could get the same numbers. And then of course I use this function here, argmax, to pull out the index that I'm looking for, and that gives me the next letter in my word. And once I hit another period, then I break. I've done with that word. I can go and get another word. I'm going to get 20 words here. So if I was to run this guy here, do it here, .py, we'll see that it does those 150 iterations. You can see that the loss is going less and less and less, so it's getting better and better and better all the time. And then it produces 20 new names. Now, some of these names are really terrible, but some of them aren't bad. Like this one, Kanabi. This, when I saw this the first time, I thought it was like Obi-Wan Kenobi from Star Wars, but Kanabi, maybe that's a good name. I don't know. Arlie might be a good name. Enna, or Janan, or Sakira. Ko could be a good name, or I don't know, this one here is Zictia. So some of the names are really, actually they're really not that bad. But you notice the last loss we got was 2.46, and in our original, in the previous video, just by counting, we ended up with 2.45. So we're close to, excuse me, we're close to what we had in just by counting. But just by counting, we can never do any better than 2.45. Whereas this way, with our neural network, we can expand our neural network. We can implement all kinds of neat features to try to lower that loss to surpass, to get even better than just by counting. All right, let's take a couple of minutes and go through the C program I put together that does the same thing. Let me just start another window here. And I think my C program here, what did I call this? P22. Let me go right to the bottom of it, where I look at the main function here. Oh, I think I went past it. Okay. Okay, so let's take a look at our C program to see how it is kind of very similar, to our Python program. Of course, it's a lot longer. So what I'm doing, I start off by creating this random number generator pointer here that I'm using, which is, again, I'm using the GNU scientific library, the same as I'm using in the Python program. So I get the names here. I get my alphabet. Remember, my alphabet is just a string of 27 characters. And the length of my alphabet is 27. And the number of bigrams is going to be the string length of names minus 1. So this is going to be like 228,000 and something is the number of bigrams. And then what I do is I encode all of these names just into integers. So for example, the letter E will be encoded as a 5. The letter M will be encoded as 13. Okay. Then what I want to do is I want to make these inputs and outputs, and these are the ones that are going to be one-hot encoding. Okay. So what I do is I put all of these numbers into these lists. So this list, this X list contains all of the X numbers, the input numbers, and the Y list contains all of the output numbers. Okay. And I even have here a function I wrote here that allows me to print out the one-hot encoding. So why don't I just do that just to show you how that works. What I'll do is I'll print out the encoding here. I'm only going to print out, let's say, the first 20 bigrams or the first 20 X values encoded in a one-hot form. And then I'm just going to exit my program here. I won't bother going any further. So let's just see how this works. So I'll go GCC minus WALL 2 minus LM minus LGSL. Okay. So if I run it, and you can see how I got this one-hot encoding here. And the reason it looks like this with these kind of XXX here is because I printed it out in a form that's understandable by GNU plot. So I can actually use GNU plot to plot these guys out. So you see the very first character is a 0, which is a period, and then the second one is E for Emma, which is a 5. Okay, so if I look at this guy using this GNU plot program, where is it here? I think it's one-hot .gp. I think I can look at it like this, and there it gives me and this again, this only gives me the first 20, 0 to 19 of one-hot encoding. So it starts with a period, and then E, and then MMA period. So that's like Emma period. And then it goes to the next word, which is Olivia, OLIVIA period. Okay. So that's one way we can look at these one-hot values. Remember, there's going to be 228,000, so it's going to be a gigantic array. And I can also do, if I look at that program, onehot.gp, this is my GNU plot program that'll do this for me. But I can also do it, I can also show it to you as ones and zeros by commenting this line out and then uncommenting this line. So if I was to run it now, it gives me a picture like this. Instead of just a graphical picture, it gives me that. So you can see I have a 1 here for the dot, and then I have a 1 over here for E for Emma, and then MM, and then I'm back to an A here. Okay, so that's how the thing is encoded. Okay, so if I go back to my program here, let me comment these guys out here. Oops. I keep forgetting what a comment is, and it's switching back and forth. So I do the one-hot encoding, and then I go into my loop of 150 here. So this is my main loop. So I first do the matrix multiplication here. So I've written a function here that does matrix multiplication. If I go all the way back up, it's just a very, like, I tried not to use any, here's multiply A times B, just straight matrix multiplication, if and only if AJ equals BI, or the number of rows equals number of columns, and so on, whatever. And that's it. So, okay, so I compute the log counts, and then I call softmax. I wrote my own softmax. Remember what softmax does? It takes the log counts, changes them into probabilities. So I end up with probabilities here. Okay, and then what I do is I'm doing here my own back propagation by getting the gradients, the changes in the W array, and then I update the W array here with the gradients. Okay, that's all part of back propagation, which I had to do myself manually because there's no function in C that'll do that for me. But when I start talking about back propagation, I'll go over that. Now, once I go through this loop 150 times, then my weight table should be fairly good, and I can go into MakeMore. And the MakeMore function I have will make 20 more words or names, and the MakeMore looks like this. It's fairly messy, but basically what I do here is I do one hot encoding of one row, and again I'm multiplying here just basically a vector here times an array. So see, the size of my vector is one row by length of alpha. I'm multiplying it by 27 by 27. Length of alpha is 27. And then I'm calling softmax to get the probabilities. And but my probabilities here are floats. And unfortunately, this multinomial function in the GNU standard library requires the probabilities to be doubles here. Requires the probabilities. So what I had to do was I had to convert these float probabilities to double probabilities I wrote my own little function called probs to doubles. And no, for you amateur C programmers, you can't just cast it. Won't work. So I convert those float probabilities to doubles. And by the way, why did I stick with floats? I tried to stick with floats all the time because that's what Python, PyTorch uses floats everywhere. They either use integers or they use floats. I've never seen them use any doubles anywhere. At least so far I haven't. So once we run this multinomial function, giving it our probability distribution, we are going to take a sample. We're going to take one sample out of that probability distribution, and that's going to be our first character. And we're going to go through that loop until we hit a period, and we're going to break, and then we're going to print out some more words. We're going to print out 20 words. So let's see how this works. Let me compile this guy again. Clear out this guy. Once I got out. And you notice how slow it's going here. Now, while it's doing that, let me show you one thing I've used here to test my system. I actually used this software monitor to test here. So you can see, for example, I always look at my memory to make sure my memory isn't getting out of hand. If I have a memory leak or something, I would be able to see that my memory is going to be going up and up and up, and it's just going to go crazy. So I use this to look at my memory. The other thing you'll notice in this monitor is that I'm only using one CPU here. Which one am I at here? There should be one that's 100%, or yeah, CPU 10 was 100%, 99. So it does switch from CPU to CPU, but it's usually only one CPU that's doing all the work. Okay, so that's why it's going so slow, is because it's just doing one. And remember, it's multiplying. I'm doing my own multiplication here of 228,000 rows and 27 columns. So my array size is 228K by 228K by 27. So it's a gigantic, for me anyway, it's a gigantic array, and doing the multiplication does take time. But there is one trick that I used to speed it up a bit. I introduced a little bit of optimization when I did my compile. Okay, so let's let this thing run out and see how it does it. On the other hand, looking at the Python program immediately makes use of all my CPUs. So it runs like super fast compared to this C program, which is using just one CPU. And again, I keep my eyes on the memory to make sure that it doesn't go too crazy, because I'm doing everything with dynamic memory allocation, which is I'm using like malloc, calloc, and free, and I just hope that I free exactly what I allocate. So anyway, there we go. You can see my resultant loss is 2.46, which is the same as the Python program. Let me bring that up here. Where is the Python program? I think that's here. So this is on the left side here, I have the Python program, which gives me 2.4 Python program. Let me change this here. Python program gives me 2.466, and my C program gives me 2.465, or I guess I could, this 5.8 might be rounded up to a 6, I guess. But you notice the generated words here by the Python program are exactly identical to the generated words of my C program. Okay, so that kind of tells me that all my backpropagation functions are working properly. So far so good. One other thing I want to show you is, let me take a look at, let me close this window here, make this window a little bit smaller. I want to run this Python program and show you how it uses up all my CPUs. I'll just run this again, the Python program, and just watch what it does here. Check out the CPU usage here. You can see all my CPUs are going crazy here. They're all going nuts. They're all computing all these matrix multiplication, and it's over. It's done. It's just absolutely incredible how this PyTorch takes advantage. Now, I could also, instead of using all my CPUs, I could have used my video card and to use CUDA processors. But I won't get into that, since I'm not really interested in that aspect of these machine learning. But I just wanted to show you that it is amazing how that Python code actually just rips through by just using all the CPUs I have, which is absolutely amazing. Anyway, what I want to do now is I just want to close everything here, and I want to start talking about backpropagation, how it works, and how I implemented that in my C program. Well, okay, the time has come where we have to start talking about gradient descent and backpropagation. So where do we begin? Let's take a look first at what we have so far. Let's get my little drawing board out here so we can make some pictures. So we started with let me change that color here to something better. Okay, we started with an input here, which was our X, our inputs, and they were all one hot encoded. So they were all like 0, 0, 1, 0, 0, 0, 1, 0, 0, and so on. So they were basically, this array here was about 200K by 27. And what we did was we multiplied that by our weights. And our weights are 27 by 27. And remember, our weights, we just set them up as random. Basically floating point numbers, random. And when we multiply X times W, we ended up with our Y predicted values, which again are about 200K rows and 27 columns. And again, like this, so this first row here, all these values, these are all floats. And if our weight matrix here was perfectly correct, then our X values here would be the same as our Y P values. I mean, that would be the perfect condition. I guess we'd just say all our random would just be all ones or something, I guess. If they were all just all ones, I guess that's what we would get. So the basic formula here is that YP is equal to like WX. In fact, you can think from your high school days how you used to have just an equation of a line would just be Y equals mx plus b, where m would be the slope and b would be like the y-intercept, something like that. In our case, this b we're not using. Well, I don't know. Let's see. That's not right here. I'll just say this b is not applicable for in this example that we're working on. So anyway, we have one equation here, and we also have another equation, which is our loss. Our loss equation really is equal to, and there's a lot of different ways I guess you can calculate the loss, but we're going to just use mean squared error loss. Sometimes they call it quadratic loss or mean squared error. That's the same thing. But I guess you could kind of look at it like this, as saying y prime minus y squared, something like that. So these are basically the two kind of formulas we're going to use. And what are we trying to do here? What we're trying to do is we're trying to find how to adjust this W matrix, how to adjust it so that we get better values of Y in our output. Okay, so what we have to do is we need to calculate the change in the loss with respect to W. Like, so for example, I guess we could look at it like this. We could say what we're looking for, okay, what we're looking for is the change in the loss with respect to W. So that's why I'm using these partial derivative notation for that. And I could say that that's really equal to the change in the loss with respect to Y predicted and change in Y predicted with respect to the change in W. So this is what we call the chain rule. And if you look at the way the chain rule works, is I guess you can just these two are crossed out, so you're left with dl over dw. So what we want to work out is we want to work out these two partial derivatives. So, for example, this if you look at this equation number 1, and this is equation number 2. From equation number 1, when you say yp is equal to wx, then you can say the partial derivative of yp with respect to w is just simply equal to x. If you remember your high school how to do derivatives. So we have this part here is just x, which is our input. But now we have to calculate this this guy here, which is the derivative of the loss with respect to y predicted. So if you look at our equation number 2 up here, our loss is equal to that. I mean, we could, just to simplify things, I could say loss is equal to yp minus y squared. So yp is our predicted value, y is our target or our labels. And to make it even simpler, I could say loss is equal to 1/2 yp minus y squared. And the reason I put that half in there is that when I take the derivative, it will kind of disappear, because this is equal to 1/2 yp squared minus ypy minus or plus y squared. So I could just go further with that and say equals yp squared over 2 minus yp y over 2 plus y squared over 2. I think that should be a 2 in there, I think. So if we do the derivative of the loss with respect to yp, we just end up with yp minus y. Very straightforward. So now we have both of these. We have this guy here, and we have this guy here. So that means that our loss with respect to w is just going to be, for example, yp minus y, basically the sum of that over n times x. Going to get something like that will be our answer. Okay, how do we? So what exactly are we measuring here? Well, we're measuring. We want to know how much or what kind of a tiny change in W will give us a better loss, or a loss that goes closer down to zero. And so basically that's all we're doing. So I think what I've done, I don't know if I've done this before. I probably got it wrong anyway, but let me see here. I tried to put it together like this, and so again, just to refresh your mind, your memory, we started off with bigrams, we encoded them, then we one-hot encoded further, and then we multiplied these together. So this was multiplied here to give us the result of our bigrams, of our predicted value. And then I've written out here just how we do the forward pass. So the forward pass, we just go just like this. This is our forward pass. And in our case, B is not applicable. I just say we're not using B. Okay. But then our backward pass, what we want to do is we want to get the loss with respect to W, and then once we get this small change in W, we can then go and we can say, well, our new W, our new weight is going to be the old W plus the DL dW, and that could make it, the old weight, go up or go down in the proper direction to give us a better loss. So I hope that sort of makes a little bit of sense. But what we'll do, let's take a look at some of the code now, and see how it works in real life. So let me bring this over here to terminal. Change directory to MM2. Okay, so let's take a look at the program here. Actually, you know what? Maybe I'll use the just the X editor here. So where do I have it here? File, open. I'll just go down here to, and I'll just go to here. Okay, so if we go to our main function here, you can see our main function. I go through, I set up my random number generators here. Now I'm not, this line here, I'm not using it yet, but this is the random number generator here to make my W initial weights. And I do that right down here by saying I make this table here 27 by 27. Okay. And once again, I did verify that these random numbers are generated exactly identical to the random numbers that were generated in the Python program. So my W in my Python program is the same as, initially it's the same as a W here in the C program. And so anyway, so here's my basically forward pass. You see, the first thing I do is I multiply the input by the weights. Multiply the input by the weights, convert them to probabilities using softmax, and I print out the loss here. and then I go and I do backward propagation just by getting the gradients. Okay, which is basically these gradients are the changes I need to make to the weights, to the 27 by 27 weights array. And once I get the gradients, then I can do an update of the weights with the gradients. And I can then do this 150 times to keep lowering my loss until I get to the point where I'm happy with the loss, and then I can jump out of this loop and I can make more. Names. So the only interesting part here is this function here, get gradients. You can look it up here, right here, and you see how I calculate the loss with respect to y predicted, and in order to do that multiplication, I have to transpose x. So I have x transpose here, and then I can do the multiplication of x by dl dy. And in the end, I just divide them all by a number of bigrams, which again is that 200. And this, by the way, is just called batch gradient descent, because I'm just treating all my input as one gigantic batch, which is 228,000 rows by 27 columns. So I just do this over and over again, and that just keeps adjusting the weights. And I just keep down here, I just keep updating the weights, and my loss gets less and less and less all the time. Okay. Some of the other functions I use here, well, this is like for MakeMore. I don't know if we went over it, but basically with MakeMore, I'm just going into that. I'm using that W array as my probabilities, and I sample those probabilities. It's basically one character at a time, and I just print out some new words. So this is my update function here. So I just take my new weights are going to be equal to the old weights. Oh, and here's another thing I didn't mention yet, was the learning rate. The learning rate, basically, I set it here to, what's my learning rate? I guess I just have it in my update. Yeah, my learning rate here is set to -50. This is just basically telling me how fast I want to go to approach the minimum loss. Now, one problem with the learning rate is that if you approach the minimum loss too quickly, you could overshoot. So that's one problem. The other problem is if you approach the minimum loss too slowly, you're just using CPU cycles that maybe are not necessary. So finding the proper learning rate for your particular model is, I think it's more of an art instead of a science. At least that's kind of the picture I get. There are a lot of techniques people use to try to find what the optimum learning rate is for your particular model. And of course, we'll get into learning rate in a lot more detail in the next videos. So we have to get gradients. We have a transpose function here. Get loss. Remember how we get the loss? We just do the the logs of all the probabilities, and then we negate that and we divide it by the total number of bigrams. So softmax, remember the softmax function, it just gets the counts and uses the counts to get the probabilities. So we get counts first, and then we get the probabilities using the counts. Getting the probabilities here, getting the counts function. Here's our matrix multiplication function. And then I have a bunch of print functions in here too. Well, this print function here will just print out any matrix I want. Make table, this is one to create the, basically this function is used to create the W table randomly. This function converts floats to doubles. I need that for whenever I'm making new names, I'm using that in the multinomial here. I need to use doubles here. So that's why I had to convert the floating point probabilities. I had to convert them to double probabilities. Some of the other functions I had here, one-hot encoding. This function is to print it in a form that GNU plot understands, so I could plot it out. And then here's the actual one-hot encoding function that does that. Make XY, this one makes the two vectors, the X vector and the Y vector. X is the input, and Y is the expected output, or the targets, or the labels, I guess you could call them too. Encoding, just changing the letter A to a 1, the letter E to a 5, a period to a 0, and so on. Getting the alphabet. Remember, the alphabet is basically, since we're using 27, our alphabet is 27, but we have 26 lowercase letters and a period. And then we have our function here. The first one is to get the names from the file. Get all the names from the file. And that's basically it. Now I just want to go through this guy. If I go to just to compile this guy, P22 minus LW minus GSL. If I just compile it like this, oops, minus the L, that should be math, sorry, math library, not the W library. If I just compile it like that and I run it, you'll notice that it runs really slow. Or is it running slow? No, it's not running too slow. I don't know if it's running. It seems to be running fairly fast. Let me just break this, run the let me run the Python program, do it 1A, and see the difference in the speed of the Python program is much quicker. But one way we can make the C program a little bit faster is just to introduce just a tiny little bit of optimization by introducing minus capital O. And that gives us, I believe, a little bit faster. You can see that it's going a little bit quicker. Okay. Still, it's no comparison to the Python program. Anyway, I won't let it go further. Anyway, so that's basically the ending of of this particular video, we've made a very basic neural network. So we'll actually, I don't know if I did this right or not, but we'll see. Anyway, in our next video, we're going to really enhance our neural network with all kinds of new parameters, new techniques to make the network perform better. So until then, keep programming, and we'll see you later.